All right, let me share my screen. All right, welcome guys. So here we are, chapter 9. We've gotten all this math done. We talked about state spaces and qubits and individual qubit gates. And so now we're gonna try and do something useful with these circuits. So let's go through chapter 9. And I know that on the first reading, I definitely had difficulty understanding what I just saw. So we'll see. If we get through the whole chapter, great. If we don't, then that's also fine. We can just pick up where we left off next week. All right, so section 1, author talks about, hey, we've talked about lots of different gates, and if you're using a particular hardware implementation of a quantum computer, you may not have every one of these, and you can implement some of these by, using combinations of other gates and whatnot. And then in theory, it requires an infinite number of gates in order to do everything. Even just like the one gate that does a rotation, there's an infinite number of angles you could rotate. So you could never exactly implement that with a finite number of gates. I don't think the term is that important, but in section 9.2, author defines quantum register, and then a quantum circuit defined as a sequence of gates operating on the qubits of your quantum register. So mostly I think register is just a convenient term, and then register size is something we'll talk about, because if they can't build big quantum computers, then if the max register size on your quantum computer is, let's say, 30, then that's going to severely limit the kinds of things you can do. And so 9.2.1, we can pause and see if there's any discussion there, but we're starting with some small circuits. So just, some ones that do measurement, or, just a very small thing, flip one bit, identity operation, just to get, people comfortable with things. And then 9.2.2, a further reminder that things in the quantum world aren't exactly intuitive to our classical macro intuition. So it shows an example where a controlled Z gate that has the control on the top is, in fact, from a quantum computing perspective, identical to a controlled Z gate where the control bit's on the bottom. So like that's just kind of super weird. And so I'll just leave it at that, just super weird. Section 9.3, the C0 gate acts like an XOR. If you think about the inputs as being ones and zeros. And the author also shows that if you don't want to overwrite one of your inputs, you can actually use 2 C0 gates, and you can put that XOR into a third qubit that was initialized with ket 0. And there's this note that when we add a qubit for temporary results or for outputs, it's called an ancilla qubit. So let's see here, some more examples using CC0. You can create a NAND type operation, and then there's some other combinations with the quantum X gate just to see what actually happens if you do these. So then finally, some more examples where up to depth 5, some different things using C0 and the Hadamard gate. And so now we're starting to do some real computation with these. And then section 9.3.3 does a proof by contradiction, showing that there's no way you can create a clone circuit that clones the state of a qubit, because basically it proves that it's not a unitary operation. All right, let me just pause here. Any comments, questions? We're about to get to the hairy stuff. Okay. 9.3.4.
Well,
this is where. Yeah, please.
Oh, sorry, Ted. It's Steve. Just a small comment. in my reading of this chapter, uh, I was sort of trying to overlay the process I would go through to program an ASIC or a FPGA, um, because it's basically the software configuration of gates, and to see the analogies. And I don't know if anybody else felt the same way about it, but it seems like most of it is the same as you would for a regular electrical circuit,
Mhm.
but there are a couple of differences in terminology that
Yeah,
wasn't quite sure about.
that's the mental model that I have as well. So obviously, if you go and you buy a I don't even know what to call it, a normal hardwired chip that does something like, it adds two numbers or whatever, then it's just sort of hardwired what the gates are. But if you have something like an FPGA, you can externally program it to set up what exactly the gates should be, connecting which inputs. And that's exactly what we do here, is we set up the quantum computer like you set up an FPGA. You say, I'm going to have these inputs connected to these types of gates, and then when I'm done, presumably, I'm going to do something with the output. So that's exactly the mental model that I have for quantum computer.
Okay, good. And is I'm wondering if I missed it or if it's in the references here. Is there a software equivalent of like a Verilog or something like that where we could actually try to build an adder,
I'm
quantum
not
adder?
I'm not sure what functionality you're referring to in terms of the Verilog. I've heard of Verilog, but I don't know the details of exactly. There's varying levels of support in the different packages um, that support quantum computing. It's still relatively early, so I would say, as a general rule, like, the support is fairly limited, right? You absolutely, in any of these languages, can just say, I start with a register with 4 qubits. Now, the first thing I want you to do is to apply an H gate to qubit 0. I want you to then apply, a controlled NOT gate between qubit 0 and qubit 1, whatever. Like, you can absolutely do that, but that's like a very manual, low level specification of what you want. I don't, um, I see announcements, so I'm sure people are trying to make things a little bit more high level, a little bit easier, but most of the discussion I've seen, at least, is at that very super low level conceptual. But maybe there's the ability to kind of like have subroutines or something that's a little less manual. Like, if you want to do something, if you say, I want to apply an H gate to each one of my 4 inputs, like, does that require you to list 4 things, or can you at least do a loop or something? I'm not exactly sure.
Okay, well, thanks. I just wanted to make sure I'm Johnny come lately, so apologies for uh,
No, that's a good question. So I
starting in the
haven't
middle.
done too much playing around yet with the different, IBM, Qiskit and some of these other things or whatever. Um, this book is definitely focused on just understanding the underlying, what's under the hood, how it works. Not necessarily there's a chapter at the end that talks about implementation, but but it's really focused on, hey, I want you to understand that this isn't, so that it's not just some black magic for you. It's not really meant to be, hey, you as the, like, software guy about to actually program this, let me get you a leg up, right? That would probably be a different book.
Gotcha. Thanks.
Yeah, cool. All right, so let's talk about section 934, our first, what I would consider really weird result. I mean, everything we've seen before, now it's like, okay, you could implement a NAND or an XOR type function uh, using quantum gates. Okay, that's not weird. So the way the author frames it, and there are other ways people frame it, but you start with 3 qubits. You call it mine, yours, and Q that we don't actually really care about. So the intent is to transfer the quantum state of M to Y. And the interesting thing is that this can be done without y needing to be near m after the initial portion of this algorithm, after the initial entanglement. So in the end, what we do is we take the state of Q, we add it to our system, which means we do the tensor product of Q with our my state. And there's a long set of equations in the chapter, in the section, that shows that if you measure the result in the, big phi plus, big phi minus basis, in the QM big phi basis, we get 4 possible results. And these are going to be classical results. You're either going to get 0, 0, 0, 1, 1, 0, or 1, 1. You're not going to learn anything about the state, right? You can't do that when you measure. You just get classical bits out. And based on those 4 results, we will tell the second person what to do with their y qubit. And after they do that, it will be in the original state of M. So that was me in very few sentences summarizing, the however many pages and the completely gnarly thing. So what this means is that if you and I are together and we have some entangled qubits, again, there's different formulations, then you can go as far away as you want, and then basically I can do an operation, call you up on a phone and say, do this or that, and then somehow, seemingly very mysteriously to me, even though my qubit is whatever and may have changed as whatever, that you way the heck over there somehow now have a qubit that's in the same state that mine was in. By the way, mine's no longer in that state. I've measured Q and M, and so it's either a 0 or 1 at this point because I've measured it. So comments, questions about the concept, about the long string of equations in the book? What do you guys think about quantum teleportation?
I agree with the previous guy. I wish there would be way to play with it.
Maya, I see you went off mute, but I don't know if your microphone's far from your mouth because we're not hearing you.
Yeah, sorry. I said I agree with the previous guy. I would like it to be implemented so I could play with it.
Okay, well, there actually is a different formulation, but that actually shows a very simple circuit. It's a different formulation. Let me see if I even still have that window open. Yeah. So I can put this in the notes. I can, but I'll start just by putting it in the chat. Okay. So this circuit, this is a slightly different formulation, okay? So, but this circuit basically says that we're gonna have 2 entangled qubits that are in the plus state. And this guy up here, this is equivalent to M. This is my thingy-bobber, okay? So you take your entangled qubit and you go off wherever the heck you want, all right? I can then do anything I want with this qubit to change the state, do whatever to it. But once I'm happy that I have some intermediate state that you don't know about, I do a C0, controlled not, and I do a Hadamard gate, and then I measure this one, I measure that one. Again, I get one of 4 classic outputs, 0, 0, 0, 1, 1, 0, 1, 1. You conditionally perform an X and a Z based on what I tell you from these 4 outputs. And when you are done, you will have your qubit in exactly the state that mine was before I did the C0 and the Hadamard. Does that help, Maya?
Actually, yes.
Yeah. So the crazy thing about this is that this qubit here, right? Like, so the state can be represented by two complex numbers. So there's obviously an infinitely number of these, but it's even like you know, whatever, R2, what is that, aleph 1, aleph 2, I don't know, whatever, in terms of like infinitely many states that it could be in, and we only told it 2 classical bits. So, you know, we gave it one of 4 answers, and somehow that reduced it from this perfectly known state to one of very infinitely many quantum states. Super duper weird.
It's actually very, very weird. Can we give like an example? So let's try to think of phi, for example, as 1 or a 0, and just try to see where we go in the circuit.
There's some static, so I didn't quite hear. I heard you asking, could we see something with like 1s and 0s to see what happens? I don't know if it's easier for you to type it, or if you want to just try repeating it.
Yep. Am I audible now?
I hear you, but unfortunately, there's a lot of static.
Okay, I guess it's better now.
Oh yeah.
Okay, so sorry for that. When I charge my phone, it's like doing that noise. I'm very sorry for that. So basically, I was saying that can we like give a 1 or a 0 instead of the phi to see where the circuit will lead us to at the end?
1 or a 0, you talking about this z and this x, or are you talking about somewhere else?
Yep, from the beginning. Yeah.
Oh, so actually,
Yeah,
well,
it's like confusing.
I can go to the book, but so the idea is actually it doesn't even have to be a 1 or 0. It can just be A of ket 0 plus B ket 1. Okay, and then we're going to do these 2 operations, and we're going to get either 0 0 for z and x, 0 1 for z and x, 1 0, or 1 1. And then let's just say we get 0 0. Okay, and by the way, this business of what we get, like 0s or 1s, is like it's kind of random. Like it like we have like a 1 in 4 chance of getting any of those. So it doesn't, not really even meaningful which one we got. That's like what's even more nuts about this. It's not technically 2 bits worth of information, because no matter what it's not like if this state is a particular state, then you're going to get 0 0, and if it's a different state, you're going to get 1 0. No matter what your input state is for psi, you have a 1/4 chance of getting 0 0 and a 1/4 chance of getting 0 1, and so on. So but let's just say we got 0 0. Okay, if you get 0 0, then that means do nothing here. You don't do the x, you don't do the z. Okay, so what that means is that if we know that we happen to get 0 0, then this thing, which was two real numbers, you know, I'm sorry, yeah, 2 real numbers, 2 complex numbers representing this state, all we did was apply 2 gates to it and measure it. And yet, at that point, magically, this thing, I say magically, this thing, which was in this known plus ket state, is now exactly A times ket 0 plus B times ket 1, without us even having applied any gates, because in the 0 0 case, you don't do anything. Is that
that's very
that nice and even
and
weirder?
I understand it more. Thank you.
Yeah. So hold on a second. In the book, where is it? Just teleportation. So in the book, they have this wonderful long list of equations. Okay, but what they tell you we started was, again, I can't remember if they use A and B or alpha, beta, whatever. They use A and B. Um, um, uh, oh, so actually, sorry, this I got things mixed up here. So actually, we're not copying M, we're copying Q. So you bring Q into the mix, and Q is you know, probability A squared that it's a 0, probability B squared that it's a 1. So you start with A and B, and they're actually complex numbers. I just said it like they're real, but and so then you go through this series of equations to prove that each of these is equivalent to the one above. And so whereas you started with a state of A ket 0 and B ket 1, at the end of it, what you will have here is I think we need to go some more equations. Yeah. So basically we have an A and a B, but the signs or whatever might be messed up, and that's why we might need to do the X gate, we might need to do the Z gate. Those, then we will completely restore it to exactly A times ket 0 and B times ket 1. So I mean that's like so.
So we don't care of the state of our qubit, right?
So in this diagram, so this is Q over here, this is M, and this is Y. And so M and Y are initialized to be entangled in the plus state. I don't know if that answered your question.
So I was asking, so if M really make a do need to be something, so Q will be transferred to Y, right?
Yeah,
so does
Q will
M
be transferred to Y, correct?
Okay, great. So does M need to be in any particular state, or it does
Yes.
not?
Yes,
Okay.
M and Y are initially entangled in the plus state. And so in fact, if I go back to my notes are wrong here. So we're transferring Q to Y. Okay. And Y does not need to be near Q after the initial entanglement with M. All right, so let me talk about this note that I added from some of the other readings, which it's not going to make this completely make sense, but it might make it a little bit more I don't know, structured as to what's going on. So what we are doing in this business is we build a 3-qubit state, but we're measuring only 2 of them. Okay, so we're measuring a subset of our complete system, and based on the results of those measurements, we're performing additional operations. So we're not all the way done when we do this measurement. And so one of the things that I read is that taking a measurement of a portion of a subset of a quantum system is a potentially unintuitive, like not obvious thing. Okay, so let's say we start with a ket psi, and it's 2 qubits, and so it has, you know, A times 0 0, B times 0 1, C 0 1 0, D times 1 1. All right, and before we do anything, the second qubit has a probability of I should actually have like norm bars on these, absolute value bars on these, absolute value of A squared. I keep forgetting these are complex numbers. An absolute value of C squared. So I'll fix all the other formulas later. But the whole point is that the second qubit, right? Second qubit's a 0 here, so it's got A, and a 0 here, so it's got C. So you have to sum those two probabilities. And the second qubit's probability of being a 1, you use the B and you use the D. So you have A squared plus C squared and B squared plus D squared for getting a 1. If we then measure the first qubit and we get a 0, that leaves the second qubit in the state A times, ket 0 plus B ket 1. And then you have to normalize it and divide by A squared plus B squared. But so basically, our probability was A squared plus C squared, and it's now dropped basically to A. If we get a 1 when we measure the first qubit, then it actually leaves the second qubit in a completely different state where its probability C and D, and again, you have to normalize them so that their squares add up to 1. So measuring the first qubit changes the second qubit's probabilities in the classic sense. And not only that, but depending on what the measurement was, it changes it differently. So I'll give a probability analogy, which is that, like in San Diego, we don't have storms that often. So the probability of thunder is low and the probability of lightning is low. But these probabilities act classically. And so you can say basically like, but they're highly dependent. And so if you measure lightning and you get a 1, there might be 99% or might even be fully 1. Okay, so whether you measure the lightning and get a 0 or whether you measure the lightning and get a 1, you can say to yourself, well, that sort of changes my probability of thunder. Okay, but here's the thing. You could have measured the thunder first without measuring the lightning and you would have gotten the same result. Okay, what you can say to yourself is that there's actually a hidden state, and that latent state of whether or not there's a storm is what has a low probability. But once you have a hidden state of 1 for there's a storm, then both lightning and thunder will match. Okay. What's different here is that measuring the second qubit wouldn't give you the same result if you hadn't measured the first qubit first. That's the key thing here. Okay. So then the same thing, just using some concrete numbers. If instead of 4, I only use 2 of them, and I say it's 0.6 times ket 0, 1 and 0.8 times ket 1, 0, then the probability of the first qubit is being 0 is 36%. If, however, we measure and we get a 0, then the second qubit is guaranteed to be a 1. It's 100% going to be a 1. And the probability of the first qubit being 1 is 64%. That will leave the second qubit in 0 because, again, there's 1, 0. There is no 1, 1. So in this example, the probabilities of the second qubit, which if you had measured it up front, would have been 64%, 34% before we did anything with qubit 1. But because we measured qubit 1, it changed from 64, 34 to either 100, 0 or 0, 100. And which it changed to depends on what we got from the first measurement. And remember, the first measurement's just random. So it's not like the first measurement is telling us some secret, whatever. All right. I don't know if that, does that help, just in terms of, again, it's not intuitive in the classical sense, but does it help as sort of a building block to know that measuring something, a subset of a quantum system, is going to change the remainder of the quantum system? In the classical sense, that doesn't happen. If I have 4 apples and I measure one of the apples, the other 3 apples don't change. But in this case, measuring one part of a quantum subsystem does change the rest of it. And that's the phenomenon that allows this teleportation to happen, is that we're measuring something and fundamentally that is changing the Y qubit in a way that we end up with the initial state that Q was in. All right. Some of the other reading I saw said that there's some misconceptions. So one of them is, does this allow communication faster than the speed of light? And I'll get to the question in just a second. And the answer is no, because even though you can be farther apart than the speed of light, and the qubit Y will sort of, I don't know the right word, instantly have the original state of Q. The reason why it doesn't violate it is because I had to tell you whether I got 0001 1011, and that required a speed of light classical communication for me to text you, call you, whatever, to tell you which of the four things that I got. And so even though a whole lot of sort of information, ended up over there, it didn't happen faster than the speed of light. Ryan asked, can you only measure one thing at a time, or is there some ability to measure multiple at once? Yeah, I think I don't think it's discussed in this book, but just in general, with quantum mechanical stuff, you can basically entangle two, I'll say qubits, but whatever. You can entangle two qubits, and then you can synchronize your clocks and move far enough away such that, let's say, you're more than 1 light hour apart. And then if your clocks are accurate to the second, then if you agree to both measure at the same time, then you are a light hour apart, yet you're measuring less than that. So the communication can't really happen. And the experiments show that basically if you do that, and let's say the two qubits are entangled to this plus state where it's either 0001, that means you're always going to get the same answer. So you can repeat this experiment a gazillion times, and even though you measured simultaneously such that they couldn't have communicated, you're still always going to get the same answers on both of them. And so what that defies is, in the classical sense, if there were a particle, an unknown particle that was somehow binding these two qubits, like gravity or electric field or something, then in theory you would have had to have traveled faster than the speed of light in order to get to the other qubit to tell it, because you may not be measuring it exactly simultaneously, right? And so if it could travel super duper fast, then it could say, well, you measured a hair's breadth sooner on this one and you got a 1, so I'm going to tell the other one, hey, you should return a 1. But that clearly does not seem to be happening. So this quantum stuff is not classic in the sense of hidden states, or in the sense of some hidden particle field communicating between them. Did that answer your question, Ryan? Okay, cool. All right, and then the other misconception that I read about is that they call it teleportation, but it really has nothing to do with the Star Trek transporter. So this isn't really teleporting matter. It's more teleporting information. It's teleporting state information. I suppose theoretically, if you knew enough about the quantum state, like say of a molecule, of a set of molecules, technically speaking, you could say, I am just a God knows how many, 2 to the how many trillion, state, quantum state. So if you copied all of that, then you really would be sort of cloning me, whatever. Maybe not teleporting me, cloning me, something like that. But it's definitely not the Star Trek transporter. All right. Any other questions? Anything you guys want to go through in terms of the questions in the chapter or the equations. I think covered it pretty well. It's pretty weird, even though we covered it. All right, so the next section takes a break from weird and just goes through some more building blocks. So the author shows some simple gates that can be used to define addition of 2 bits and how you deal with the carry and do all of that, and builds a circuit that can add 2 3-bit numbers. So then, goes through several pages just to show you what the outputs after each of these step 1, step 2, step 3 are, to show that in the end, here are your inputs. You've got a bunch of zeros in these ancilla bits, and then you've got, it's a 3-bit number. So X has X0, X1, and X2, and Y has Y0, Y1, and Y2. And then in the end, your output, you've got where the Y's used to be, you have the 0, 1, 2, and now the extra 3rd bit for X plus Y, since there can be a carry. All right. One thing that I read elsewhere that's not mentioned in this book is, if you notice in this diagram, basically there's the outputs that we want, but everything else other than the sum, these four qubits for our sum, everything else is returned to its initial state. So this X0 doesn't get munged into something else. And even like this extra 0 that's used as a placeholder, where they have carries or something like that, it's returned all the way back to 0 at the end. All right, and each one of these other zeros is either part of the output or it's returned. And so this is referred to as clean computation. And later on, there's the calculation. I'll try to mention it, but basically, where like things involve interference, if you don't do this, then theoretically, your thing won't work. And again, remember, like anything that happens to a portion of a quantum system can change the rest of it. So if you have this 1 0 that you changed to something else, then it could affect the rest of your things. So that's one thing that you will notice, is that these circuits that people devise, if they have ancilla qubits that aren't outputs, then they're always returning them to 0 before you finish. And sometimes that requires extra work, like you see sort of these carry inverse and stuff like that. It's, some of that may be just necessary, but some of that is purposefully organized in a way that it returns these ancilla qubits back to 0 when you're all done. Wow, over a buck per second. And that's 27 qubits, yeah. Okay, and so then the other concept here, right, is the idea that if you have a little sub-circuit, we can call this a subroutine, we can reuse it over and over again. I'm guessing that that's not really a difficult concept for people here. All right, any questions about any of the exercises, the questions, or what we're doing here? All right, section 9.5 introduces the concept of an oracle. And if you're like in computer science, you may be familiar with the term predicate, but basically it's a function that returns either true, false, or 1, 0. We'll actually see the implementation of the oracle might be slightly different, but the general idea is that it's just a true, false kind of a machine. Okay. And I will note that the name oracle got coined however many decades ago, and it's actually misleading. Okay, so the oracle tests validity, which is generally not that hard. The oracle does not know the answers in advance. So the example that I saw was traveling salesman. Traveling salesman's known to be sort of this exponential problem to say, what is the least cost route between n cities that then ends you back where you started. But if you ask the question, I did a heuristic and it said, hey, I can do this round trip in 1,000 miles. If you ask the question, is this particular round trip less than 1,000 miles? If you give it an input, the oracle can pretty easily add up the distances between the cities and answer true or false. Is it less than 1,000 miles? Okay, so that's an example of an oracle. It's not really magical or anything like that, right? The oracle has no idea which routes, if any, are less than 1,000 miles. But if you give it an input, it is very, relatively speaking, it is straightforward for it to test whether or not it meets the conditions and just return you a true or false. Okay, so don't, despite the name oracle, don't think that the oracle actually is doing anything fancy. It's just testing validity of a condition. Okay, so section 9.6 says we are going to do this useful function. We're going to do amplitude amplification. So we want to increase the probability of a single basis ket. So if you have 4 qubits in a system, okay, you have 2 to the 4th, you have 16 basis kets. All right, and you could decide that I'm going to start in an initial state where all of them have equal probability 1/16, but there's a particular qubit, you know, 0101, and I want to increase its probability and lower the probability of the other 15. Can I build a circuit that does that? And the answer turns out to be yes, you can build a circuit to do that. So how do we do that? So the first thing is we build a matrix that flips the sign of a single basis ket. Okay, and so in this case, we're now just going to talk about a hard-coded example, but eventually what we're going to do is we're going to have our oracle do this. So it's going to say, if this is a valid answer, I'm going to flip the sign. Otherwise, I'm going to leave it alone. And you can prove that this is a unitary operation, so it's legal. You know, it doesn't change the absolute values of anything because it's just flipping one sign. All right, the real hard one is this second one, which is inversion about the mean. Okay, so what we want to do is if you have the amplitudes of your different basis kets, so I've been saying 16, the book I think used maybe fewer, maybe it only had 8 or something like that. But if you have these 16 and one of them happens to have the highest probability, can you do an operation that actually increases its amplitude and slightly lowers all the other ones? And so the answer is yes. And basically, it's this inversion about the mean thing where basically, if you have things on one side of the average and things on the other side of the average, you can flip them, but in the way that it flips them, the one that's the farthest away actually gets a little bit farther, and the other ones get a little bit closer to the mean. And so they show, you know, the different pattern, the different matrix, you know, that does this and how this works. So the author states that this trick uses constructive interference, but doesn't really explain that. I read a little bit more. I have a little bit of intuition about that, but I don't know if I can necessarily explain it. So let me just pause here and see if you guys have any questions, any comments about these 2 operations, flipping the sign and then doing this inversion about the mean. And the net result of the combination of those 2 is that whichever one was the biggest is now going to get slightly bigger amplitude, slightly closer to 1, and the other ones are going to get slightly closer to 0. All right, if there aren't any comments or questions, then we'll keep going, because we talked about this because we want to use this as a tool, as a subroutine in Grover's search algorithm. So previously I was just talking about doing this for a known hard-coded basis ket. But if instead we build an oracle, and the oracle, again, it just tests our inputs, then what it does is it outputs whatever the original thing was if it doesn't meet the condition, and if it does meet the condition, it flips the sign. And so basically, if we just pass in ones, then basically, we'll have ones for everything except where there's an answer, there'll be a -1. So when we go through this, the initial formulation is, let's assume there's exactly one answer that meets the condition for what we're testing for our oracle, okay? At the end of the chapter, they go through some stuff, and it turns out that you can also handle multiple answers, but it's just easier to think about if there's only, one right answer. So basically, if this is our oracle, our U sub f, then basically this replaces our hard-coded flip that we had in the previous section. So if you run consecutively the U sub f and this U sub phi inversion about the mean circuit, then what you're going to do is you're going to bump up the amplitude of whichever answer the oracle says is the right answer. So what you do is you take, let's say it's, again, 4 bits, so there's 16 different basis kets. You take your 16 basis kets and you put them in a superposition state such that each of them has a probability of 1/16. When you pass it through this combination circuit, let's just say, what's 1/16? It's about 0.06, like that, okay? So everything is 0.06 to begin with. Once you pass it through these 2 unitary gates, what'll happen is the thing that the oracle said, yeah, that actually meets my criteria, maybe it bumps up from 0.06 to 0.1. And all the other ones bump down from 0.06 to 0.055. All right. If you run this through those 2 circuits again, then maybe that 0.1 gets bumped up to 0.15, and the other ones get bumped down from 0.055 to whatever, 0.052, right? You do it again, and now this thing gets bumped up to 0.2, and all the other ones get bumped down to 0.05. Do it again, this gets bumped up to 0.3, and those other ones get bumped down to 0.04, something like that, okay? And so then if you run this enough times, you can imagine that what you wind up with is the thing that the oracle says meets its condition, now when you measure it, has a probability of 0.99, and all the other ones have a probability of 0.001. Okay, that's the purpose of this. And so the idea is that you run this U sub f oracle and this U sub phi inversion about the mean circuit. Turns out you run it square root of n times, where n is the number of basis kets you have. And when you measure it at the end, unfortunately, it's not absolutely perfect. Like an example I gave you, I said, the amplitude is 0.99. So there's a very small chance that you will not get the answer that you want. But assuming that you have some oracle which has an easily testable thing, like, is the traveling salesman route less than 1,000 miles? Once you run this algorithm and you get an answer and it says, yeah, here's the route, go to city A and then D and then B, then C, then F, and then whatever. You just go and you look up and you see what is that route. And if it turns out that it's not under 1,000 miles, then you just simply discard it and you run the algorithm again. Okay. And it turns out that the odds of you having an error are pretty small, around 1/n. And if the assumption is you're running this on big problems, because on a small problem, you could have just done exhaustive search manually on a classic computer, then that means that the odds of getting an error shrink very rapidly. So, maybe you need to do this twice. But it's very easy if it says, oh, here's this route, go to city F, then D, then A, then B, then C. If in fact you test it and yeah, that was only 980 miles instead of 1,000 miles. Then you now know that this algorithm has successfully given you a solution to traveling salesman that's better than your original guesstimate, which was 1,000 miles. All right, so that's like procedurally what we're doing here. The book didn't really emphasize the idea of like, why would you do search in the first place, right? So imagine that you're doing search, like say for the traveling salesman problem, where there is no easy way to have a heuristic that reduces your search space, right? So like if you were searching for a word in a dictionary, you would not just use an exhaustive search starting at page 1 and then flipping through, right? You would say, I know the words are in alphabetical order, and so I can divide my search space. If I go to the middle of the book, the binary search. If I go to the middle of the book, I can exclude half of the search space, right? For traveling salesmen, there is no easy way to exclude portions of the search space. I mean, there's probably some heuristics, but you know. So for this type of thing, the only way classically you can solve this is by searching through all the different options. Actually, I didn't need to say classically. The only way you can really solve it is by going through all the search options. Classically, going through all the search options is an order n type operation. The problem is n in this case is exponential in the number of cities. Okay, so what's crazy about this quantum algorithm is that now instead of doing n searches, we can do square root of n searches, and we can exhaustively check every single one of the n things. So if we have 10,000 things in 100 searches, we will have exhaustively searched all 10,000 things, which is nuts. So maybe not quite as brain racking as teleportation, or depending on the person, maybe you think this is even more wild than teleportation. The only downside to Grover's search algorithm is that if something is exponential time and you cut it and you take the square root of that, it's still exponential time. So yes, square root is faster, and so you could solve something, you know, exponential, you know, n faster than you could on a classical computer. But basically, as soon as I go to n+1, then you're screwed. And it takes just as long as it did the classical computer to do n objects. So, okay, fine. You've increased by 1 the size of the problem that you can solve, sort of in a reasonable amount of time. Exponential's still going to kill you. All right, so that is Grover's search algorithm. Comments, questions? All right. I have a note here. So reading elsewhere, there is a geometric interpretation to doing this oracle inversion about the mean circuit. And that geometric interpretation is that it performs a rotation. So if you think about the case where you have exactly one answer, okay, the desired state, so like I said, we have these 16 of them, and 0, 1, 0, 1 is our desired answer. The desired state that we want is to have a vector, to have a state that all the other bases are 0 probability, and the 0, 1, 0, 1 answer has 100% probability, and then all the other ones after it have 0. Okay, so basically this is just the standard basis, right? It's 100% it's a 1 in that one direction, and it's a 0 in all the other directions. if we take the dot product of that vector with whatever vector we currently have, because it has all zeros in all the other ones, all of those things are going to be zero. Okay, you know, we do the position-wise products, right, and then we sum them all up. So basically, all those other things are going to be zeros, and the only thing we're going to sum is whatever our current value is in the desired basis ket. And so basically, what this proof shows is that the dot product of our initial vector and the answer that we want is going to be very small. It's going to be very close to zero because there's all zeros contributing except for this one product. Okay, and if it's very close to zero, that means that these two vectors, so to speak, are very close to orthogonal. They're not exactly orthogonal, but they're very close to orthogonal. And basically, the way the geometric interpretation goes is you can say that it's essentially like 90 degrees less some small angle delta. And then you can show that this operation is basically, it's kind of like rotating our vector by 2 delta in the direction towards the answer that we want. And I don't know, but if you do like inverse sine operations, whatever, it turns out that when it's going to get closest is going to be after you do this square root of n, repeated square root of n times. And so that's the geometric interpretation of how this algorithm works, is that it's rotating it towards the answer that we want. And the reason why there's error is because it's never going to actually necessarily exactly get you the answer you want. It'll be off by a little bit, and that's bounded by this 1 over n. What I didn't really realize reading the book, but what I saw elsewhere, is that if you repeated this more than square root of n times, it'll actually get worse. It'll keep rotating past the answer you want and rotate away from it. So this business of running it square root of n times, rounding down, that's not like, oh, run it at least this many times. It's actually run it exactly this many times, because you're going to get worse results if you run it too many times. So, so I don't know if that helps, but so somehow we have to think about this rotation being a result of like constructive interference. This amplitude amplification is somehow, you know, if you have these different waves, whatever, that you want to set up your, if you imagine like water waves or whatever, you know, you want to set up your experiment such that the thing that you want, it has crests that overlap and they positively interfere, and everywhere else, you know, things have some mix of you know, crests and valleys, and so then they end up you know, destructive interference lowering. I don't really have intuition around it, but I'm repeating that just because some of you may have a better sense for this. Some of you may have studied physics and you may understand better sort of like the Schrodinger wave equation behind this, and that may be where the interference is easier to explain, but I don't know, that's the best I got. All right. Any comments on any of that exposition? Anybody able to help me out here with this interference business? All right.
Sorry, I didn't read it. I hope, you know, I have high hopes for you.
Thank you. All right. Given the time, I think we'll just keep going. I don't know how much to say about these last two sections. So section 8 is the Deutsch-Jozsa algorithm, and it introduces a problem. Imagine you have a deck of cards, and you know that the deck is either uniform, so every card is red, or every card is black, or you know that the deck is balanced. It's half red, half black. So the question is, how would you determine whether it's uniform or whether it's balanced? So in the classic sense, you need to observe more than half of the cards. Since there's 52 cards in a deck, if you observe 27, if they're all uniform, it doesn't matter if they're black or they're red. If they're all uniform, then you know that the whole deck must be uniform. Obviously, at any point that you get a red and a black, then you know the deck must be balanced. So it's possible for you to know sooner, but the worst case is you have to measure it slightly more than half. And so the Qubit version is that it's either returning all zeros, all ones, or that it's balanced half-half 0 1s. So it goes through subsection 981, sort of talks about if you apply Hadamard gates to all of your input qubits, how can we represent this using big sigma notation? And in particular, it does a thing where it does -1 to the whateverth power, and that basically just acts as a sign change. So for even numbers, it's positive. For odd numbers, odd powers of -1, it's negative. And that gives you a more compact notation. And using that, then you can do a whole bunch of equations to show, what happens. And so then we have this circuit where we have an extra ancilla qubit, and we flip it so that it's a 1. And so then basically we have 0, 0, 0, 0, 0, 0, 1 as our inputs to the circuit. We're going to do Hadamards on every single one of these qubits, including our ancilla qubit. We're going to apply our oracle function, whatever that is, unitary matrix U sub f. Then we're going to Hadamard everything except for our ancilla qubit, and we'll measure. And basically, if when we measure, we get all 0 kets, then the oracle is constant, and otherwise it's balanced. It's not exactly clear to me how this oracle is, what kind of problem this oracle is used for, but basically what this is showing is that for a problem that in the classic sense would take you order n, just slightly over half n to do it, you can actually do it in constant time. You can do it in a single step. So obviously there's going to be few problems that you can formulate your oracle to do this specific thing of being either constant or balanced. But if you can formulate your problem such that an oracle will either be constant or balanced, then you don't even need square root of n. You can do this in a single step. Boom. So that's Deutsch Josa. Any questions? All right, the last one, I don't fully understand. I didn't go and reread all the equations, but Simon's algorithm. So we define a problem where we're looking to see if our function f of x repeats values. So if f of x for every single input value x outputs a slightly different answer, then there's no repeats. But what we're looking for is the repeats. And we're going to get to it in the next chapter, but we have this very specific formulation where we're saying the repeats won't just be at arbitrary places, but rather any time that x or y is the value r, then it'll be a repeat. I don't know yet how this formulation comes about. But if you formulate that that's the structure of your repeats, then your classical algorithm, even the square root, search for 2 to the n is still going to be super painful. But with Simon's quantum algorithm, we can find the value of r in order n time, in linear time. So we see the circuit in subsection 2. And then again, there's a bunch of analysis in subsection 3 where it walks through the cases where R is 0, where the case R is not 0. And basically it shows that for a certain value n, if you run it an extra 30 times, if you run it n plus 30 times, then the chance of failure is 1 out of 2 to the 30th, or about 1 in a billion. So, so you can just run it a few more times in order to, you know, reduce this error as tiny as you want. And so the author ends the section by noting that, whoops, I didn't actually fix this. That f of x XOR R looks a lot like f of x plus R. And when you say f of x equals f of x plus R, that defines a periodic function because it repeats every R. And so in the next chapter, we're going to see that something similar, that Simon's algorithm was the inspiration for Shor's algorithm. We're going to see something about periodic functions. I've heard other people mention this quantum Fourier transform. And basically, this will lead us to the probably most publicized, talked about algorithm. Shor's algorithm does factorization of integers. And so the idea is that if you have a composite number that is the product of two very large primes on a classical computer, there's no shortcut. You just need to do brute force, try every set of primes in order to figure out its factorization. And Shor's algorithm, I don't remember what the exact time of it is, but it's no longer exponential. It's much faster. So this will not break all cryptography, but it will break like current, you know, whatever standard RSA, you know, Diffie-Hellman public key encryption that's just based on composite numbers that are product of two primes. So anything that's designed to be hard because it's the product of two very large primes, that type of cryptography will be broken by Shor's algorithm. All right, guys. So I didn't feel comfortable after the first reading, but I do feel a little bit better now in terms of I didn't follow all the equations, everything, but I have a sense for a few things that you can do with quantum circuitry with a quantum computer that you couldn't do with a classical computer. Okay, so this teleportation thing is certainly very weird, but you can do an exhaustive search in square root of n time instead of linear time. And you can do a search with this really funky Deutsch-Jozsa type oracle where it's either constant or balanced. If you have that kind of oracle, then you can do it in constant time in the single pass. And then Simon's algorithm sort of takes this otherwise exponential problem of finding repeats in this specific formulation from exponential to linear time. And the tease is that Shor's factorization algorithm is also going to do something similar. So we're not done yet. We're going to talk about a few complex algorithms in chapter 10, but let me ask you guys, I mean, I came into this wanting to, I'm not committed to, I'm not switching to becoming a quantum computer programmer, but I wanted to understand quantum computers, understand better what they might be capable of, why having quantum computers would be interesting, how they might be useful. So we're not done yet, but do you guys feel like you now have a better sense for what kinds of things a quantum computer might be able to speed up, why it might be useful, and also some limitations that it's not just gonna like magically speed up everything? I feel like I'm a a decent way there. I can't say that I understand everything about quantum computing, but I do feel more comfortable with just like, yeah, some things I can see can do, like brute force search, do faster, and some things still not clear.
I'm not sure. It is all interesting, but you said that factorization could be done quickly now. And I'm sitting here wondering, what about elliptic curves cryptography? Because I don't understand if it helps or not for this.
What type of cryptography?
Elliptic curves?
I don't know it either. I suspect that many things are not based on just composites that are the product of two primes. Okay. I've certainly read articles that simply say, hey, if you change your cryptography from what we're currently using to any of these things, then they will be just as hard for quantum computer as things are today for classical computer. Okay, so I don't know the specifics, but I just know that there are well-known cryptographic, one-way functions that aren't vulnerable to Shor's algorithms. So basically, like if somebody tomorrow snapped their fingers, built a quantum computer that had millions of qubits and worked really great and was cheap, wasn't $1 a second, then that would not be the end of cryptography. That would just be, okay, you can't use X, Y, or Z algorithms. You have to use A, B, or C instead.
Okay,
Yeah,
I personally think that, there always will be something which you should sacrifice. Like sometimes it's memory, sometimes it's time, sometimes it is price.
mm-hmm. Yeah. But I think that the key thing is that there will always be problems that are exponential, even if you have a quantum computer. That's one of the things that I think was definitely a big question mark for me before reading this book. Like, well, if you can do factorization of integers quickly, does that then mean that it's just a matter of time before we find the right algorithm that can turn anything exponential into a linear problem? And it seems very clear that the answer is no. Not every exponential problem is going to be turned into a polynomial problem. So I think that would turn the world of computing on its head. It would have some positive implications because I'm sure there's like a lot of optimization problems. We could make the world a better place. Maybe there's like some material science people. It's like, oh, well, if I could do that exponential search in polynomial time, I could find you a, whatever, a room temperature superconductor that has all these wonderful properties. So, so yeah, I think fortunately and unfortunately, it's not going to be that kind of a game changer. All right, thanks for the link, Crystal. I'm sharing my screen, so I can't click on it, but I'm going to click on it in a second as soon as I stop sharing my screen. All right, why don't we formally end this session here? We can stop the recording. I'll stop sharing my screen.